All right, in this video we're going to talk about random variables and probability models, or probability distributions is another name for those. All right, so let's start off with some definitions here. The first definition I want to look at is random variable. Okay, a function that assigns a numerical value to each outcome in a sample space is associated with some random phenomenon. Okay, in other words, we're going to have situations of randomness, and we're going to assign values to every possible outcome in the sample space. Okay, that's what we're going to call define as a random variable. So let's look at an example here of looking at dice. Actually, just looking at one die. Okay, let's let the random variable x be defined as whatever value shows value. Good handwriting here. Value shows on a die. Okay, so the possibilities here are obviously 1, 2, 3, 4, 5, or 6. Okay, and so then we can list out the probabilities of each one of those outcomes, or each the probability of each value that the random variable can take on in this table. So we'll write 1/6 because it's 1 out of 6 for each one of these. Okay. All right, when we do that, what we've created is a probability distribution, or a probability model. The book uses the term model. I'm used to the word distribution, but I'll try and stick with what the book uses, which is model. All right. We could also graph this. Okay, so on the x-axis, we could put the outcomes 1, 2, 3, 4, 5, or 6, and then we could graph p of x on the y-axis, and that would be obviously the probabilities, and that would give us a visual, maybe even a better visual, of all the probabilities and all the outcomes. All the probabilities of a random variable associated with a random variable should add up to 1. So all these values need to add up to 1 because the random variable takes on every outcome in the sample space. Okay, so the probability should sum to 1, or 100%. Okay, let's go over here real quick. Let's talk about expected value. All right, the expected value is the long-run average of a random variable. All right, this is equivalent to asking you what's the average value of the random variable over the long term. Okay, this is also called the mean of the probability model, or probability distribution, and this Greek symbol right here is mu. Okay, so we'll denote mean in the terms of, or in the situation of expected value, with mu. All right. This is also the sum of all the x values times their corresponding probabilities. So I will oftentimes say probability times value, and you're adding up all of those numbers. All right. So let's take and do an example here. So let's find the example for rolling a fair die, and then compute the expected value for a weighted die. Okay, so let's look at a fair die. Well, the expected value, we denote that by e of x, e for expected value of the random variable x. Okay, and that is going to be equal to the probability of getting each value times the value. So we'll take 1/6 times 1, 1/6 times 2, 1/6 times 3, 1/6 times 4, and we're going to add up all of these numbers. Okay. Now, you can probably guess what the value will be. If you average up all the rolls, it should be somewhere between 3 and 4, because half of your rolls approximately should be less than 3, or 3 or less, and approximately half should be 4 or more. So the expected value will be 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3 plus 1/6 times 4 plus 1/6 times 5 plus 1/6 times 6. Okay, and if you compute that, you end up with 4.4 for the, oh sorry, no, that's the weighted one. You end up with 3.5. 3.5 for the expected value. Excuse me. So let's look at the weighted die. In the situation of the weighted die, you're going to have probabilities of 0.1 for 1 through 4, for numbers 1 through 4. But if a 5 has a 0.2 probability of showing up, and a 6 has a 0.4 probability of showing up. Therefore, you can take and do the same method, but it's not going to be 3.5. It's going to have to be higher. So if you do this in your calculator, 0.1 times 1, 0.1 times 2, and you add up all of those values, you should pause right here and try that. Make sure that it works. But you should get this value here. You should get 4.4. Now let's analyze this situation here. As a fundraiser, a student group sells 500 raffle tickets for $2 each. The drawing of the top prize will be a gift certificate of 100. Second is 50. Third place, there's 5 third place prizes, and each one of those gets a $20 gift certificate. So let's create a probability model for the situation. First, let's list out all the outcomes. Look, you can either win, so you can take first, you can take second, you can take third. Remember, there's 5 third place prizes, or you can take fourth, which is losing. Okay, a lot of people are going to lose in this situation. A lot of the 500 are going to lose. The X value, the random variable that we're going to choose here, is the amount of money that you win for each outcome. Okay, so the amount of money that you win for first place is going to be $98. And that's because you have to pay $2 to get into the game. All right, and then for second place, it's going to be $48. For third place, it's going to be $18. For fourth place, it's going to be negative $2. Okay, so if you lose $2. Let's look at the probabilities. The probability here would be 1 out of 500 because there's going to be 1 winning ticket out of the 500. There's going to be 1 second place ticket out of the 500, so that's 1 out of 500. And then you're going to take 5 out of 500 because there's 5 third place winners. All right, and then last, there's going to be a lot of losers. It's there's only going to be 7 winners, so there'll be 493 losing tickets, so 493 out of 500. Again, in your calculator, you're going to take amount times probability plus amount times probability and add up all those values. What you end up with here is the expected value is negative $1.5. Again, you should try that to make sure that you're computing it correctly. Okay, so basically, you're over the long term, you can expect to lose $1.50, which is probably clear. The odds are stacked against you greatly in this game, so you're not going to probably win money just by playing this game repeatedly. Okay, let's look at this example here. So this example, we are a golf club, or a golf course, is trying to increase the number of people that golf there on weekdays. All right, so here's the situation. If they have 4 aces laid out on the table when a player comes in to pay for their round of golf, and the 4 aces are there, so ace of diamonds, clubs, spades, and hearts. If the player turns over or draws the ace of diamonds, the player golfs for free that day and saves on the $50 fee. If the player turns over the ace of hearts, then the golfer gets to turn over another card. If the second card is the ace of diamonds, the round is half price, so that'd be $25 off, or $25 total would you'd have to pay. If the first or second card is a black ace, the player gets a $10 discount. Okay, so let's list out. We want to find the expected value of a round of golf. How much is it going to cost on average to play a round of golf? So let's figure out, first of all, the probability of drawing a diamond. Well, the probability of drawing a diamond, we'll call that P of D. That's going to be 1/4. Okay, 1 out of the 4 cards is the ace of diamonds. Remember, it's only 4 cards. It's not the whole deck. All right. Now, let's look at the probability of drawing, what's the next most straightforward one here? How about a black ace? So on the first draw, what's the probability you get a black ace? Well, there's 2 black aces out of 4, so it's 1/2. All right, so that's the probability that you draw a black ace. What are the other options? Well, you could draw the ace of hearts and then draw the diamond. Okay. Again, you should try these probabilities out to make sure that, and then check your answers with the video here. So probability of heart then diamond is going to be, well, 1/4 for the heart times, well, if I already took the ace of hearts out, there's only 3 cards left, and only one of them is the ace of diamonds. So it's going to be 1/4 times 1/3. That's 1/12. Okay. Now, what is the probability of the last option, which is that you take and draw a heart, and then you draw one of the black aces? Okay, well, that probability is, again, 1/4 to start off with, because it's 1/4 probability to get a heart, the ace of hearts. And then you're going to times that by how many black aces are left divided by the total number of cards. Well, there's 2 black aces left, and there's 3 cards total left, so times 2/3. That's going to give you 2/12, which is 1/6. Okay. Now I think we have everything we need to figure out the expected value. Let's go over here and do that. The expected value then will be the probability. We'll start just in the order that we went before. So the probability that you get a diamond, so that's 1/4, times how much are you going to have to pay if you get a diamond? Well, nothing. So 1/4 times 0. Okay? Plus the probability that you get a black card on the first or the second draw. That's 1/2. Or sorry, on the first draw. So that's 1/2. If you get a black card on the first draw, you're going to get a $10 discount. So you'll pay $40. If you get a heart and then a diamond, that's going to be a probability of 1/12. And then the amount of money that you spend then is going to be half price. So that's $25. And then last, you're going to take 1/6 times, for that one it's going to be $40. I ran out of space, sorry. So it's going to be $40 for that one, because you're going to get a black ace on the second draw, which means you get a $10 discount. When you compute that in your calculator, you get $28.75 for the expected value. All right, we're going to roll a die 4 times. We want to find the probability that we roll all 3s when we roll the die. Okay, so let's figure this out. This means that on the 4 rolls, we want to know what's the probability that we get a 3, and then a 3, and then a 3, and then a 3. All right, so that's going to be, if you think of the 4 rolls, 2, 3, 4, that's going to be 1/6, 1/6, 1/6, 1/6. Okay, on each one. And this is an and problem, right? We want that and that and that and that. So this is going to be 1/6 to the 4th power, which gives you a probability of 0.00077. It's not good. Okay. So pretty straightforward review problem there, I think. What's the probability that you get no 3s? Okay, well, the probability that you get not a 3 is 5/6. Okay, so the probability that you get no 3s is going to be 5/6 to the 4th power. Okay, again, you're thinking in terms of 4 rolls. You want 5/6 times 5/6 times 5/6 times 5/6. That's 5/6 to the 4th power. Okay, that ends up being 0.482. All right, let's make this a little bit more interesting. So we want to know now the probability that you get exactly 2 3s. Okay, so exactly 2 3s. Well, what we need to do here is figure out what are the possible outcomes, right? So we could have we could go 3, 3, and then not a 3, and then not a 3. That's one option. We could go 3, then not a 3, then 3, then not a 3. We could go not a 3, not a 3, then 3, 3. We could go 3, and there's several other examples, right? So there's many different ways that we can get exactly 2 3s, okay? How many ways? Well, we have 4 possible slots, if you will, okay? And we want to know how many ways can we pick 2 of them, okay? So 4 possible options. How many ways can I select 2? And that is going to turn out to be 6. But that's the number of ways that we can select 2 3s in this situation. Now, we're going to times that by the probability of each one. So let me write this out just so that it's a little bit more clear. I'm going to go up here. Sorry. So let's look at 3, 3, n. That probability is going to be 1/6 times 1/6 times 5/6 times 5/6. Okay? If I take and then look at n 3, 3, that probability will be 5/6 times 5/6 times 1/6 times 1/6. So all these probabilities that I laid out down here and the other ones that I didn't write out are all going to be the same. Okay? So, and I can write this probability as 5/6 squared times 1/6 squared, or reverse the order, doesn't matter, but it's going to be the same. So I'm going to take the number of possibilities times 1/6 squared times 5/6 squared. Okay? Again, because each one of these possibilities has the same probability. So it'll look like this: 1/6 squared times 5/6 squared. This turns out to be 0.1157, or about 11.57% chance of happening. Now, this situation here is a special situation probability called the binomial experiment. All right, and we don't need to do the heavy lifting of figuring out this pattern every single time. Okay, so if we had 15 rolls of the die and we wanted to know exactly 13 being 3, we need something more powerful than just listing out all the options and trying to reason our way to what the solution would be every time. Okay, so that leads into the binomial experiment formula on the next page of the notes.